So I'm going to be talking about my take on maze solving, and the reason for doing this is that we haven't done maze solving on Minos for quite a few years. We did a session of it on at Royal Holloway many years ago, where I found that everybody who said they used the same solving algorithm, when it actually came down to describing it, they used something different. So I thought I would put up what I'm currently using in case it's for anybody or got some new ideas. I'm not entirely sure where all the ideas came from, but I do know that Derek Hall certainly contributed some of them. So thank you, Derek. Right, this version of the solver is running on an STM32F072. I don't know if you can see that because I can't see what my camera can see. It's on a STM32F072 at 48 megahertz on a Nucleo board. It uses MPE's Fourth Light, which is a free download from their website. It talks to the computer over a serial lead. So what you're seeing on this screen here is it's a Teraterm terminal, so it's a VT100 terminal. So the mouse has to send cursor positioning codes and goodness knows what else. It sends it quite quickly at 921600 baud, but it does still slow things down. So this particular thing uses one of Peter's maze files. It's APEC 1988. I use the files as is, apart from copying and pasting the file name into the file so I can get it up here. Now T is the target cell. Can you see my cursor jiggling around over things? Okay, yeah. That's good, right. Okay, so T is the target cell, and I can toggle that between the set target cell and the start cell. Now, the way the solver works is via a queue. So what the solver has done already, in fact, is put the address of this cell into a queue. And when I run one cycle of the solver, what it'll do is it'll take out the top of the queue, it'll look at the 4 adjacent cells. If there's no wall in the way, it will put them back into the queue if they haven't already been in the queue, and it will mark them as solved. So those S's show that those cells have been solved. I put those in a particular order. I currently put them in north, east, south, west. So the next one in the queue will be this north one here. And when I press space again, it will take that out and have a look at the 3 adjacent cells. If there's no wall in the way, it will put those in and mark them as solved. So I can do that lots of times, and it will gradually work its way out towards the mouse. Now, the interesting bit happened when it reaches the mouse. It's going to eventually have this cell in the queue. And when it pulls it out of the queue, it's going to look at this cell, because there's no wall in the way, and say, ah, that's where the mouse is. So I can now move the mouse from where it's found it to where it's just come from. And then I reset all the solved markers, put the T back in the queue, and repeat. So if I just do this bit, you'll see the solver reach the mouse and move the mouse. Okay, so I've moved the mouse to there, and I check in my maze file to see if I can now see a wall, and I put that in where it can be seen. So each time I do that, it moves the mouse on one cell. Now, I don't know if that's too fast. Can you see the flooding out from the middle? I'm getting some nods, so I'll assume you can. So as here now, I've got no wall in front of the mouse and no wall to the side of the mouse. So the solver is going to work its way out, and it will reach this cell will go into the queue before this cell goes into the queue. So this will come out before this one does, so the mouse will turn right. Okay. and we find some more walls. Everybody happy with that so far? Good, right. So I can automate that. I can press a button and it will do that over and over again until the mouse reaches the center. And you should see that the solver is only solving the bits it has to solve. So the area that gets S's in gets less as it gets closer to the center. So I only have to look at the cells that are relevant, if you like, between the mouse and the center. I don't have to look over the entire maze. It makes it quite computationally efficient. It's quite fast at solving the maze. So if I was running this as a mouse in a maze, the next thing the mouse would do would be to reset the target square back to the start, and then run the mouse back to the start. Now you'll see there's lots of asterisks all over the place. Those are cells that the mouse has currently visited. It's been there. So anything that is next to an asterisk, if there's a wall next to it, that's a genuine wall. And if there's no wall next to it, there is a genuine absence of a wall. Now, so far, all that the solver has done is put this cell into the maze, into the queue. But you'll see this asterisk is green. That's because it's the target cell. So if the mouse was there, then the mouse knows how to get there. So the green ones are cells that the mouse has visited, that every cell that has been through the queue to get to that cell has also been visited and solved. Don't know if that makes sense. It'll make sense perhaps in a bit more. I'm going to run, do one of these. So the green cells are bits where the mouse knows that it is on what is currently a fastest route back to the target, because it's been there and the solver has reached them already. So if the mouse ever got to a green cell, it could stop solving and start doing a fast run from there using the data from the cells that it has been to. I haven't implemented that, but it's there for when I get that far with a real mouse. So if we do that a few more times, we'll see that the mouse is gradually getting closer, but it doesn't know that it doesn't know of a solution to the maze yet. It probably thinks that there is a fast route down this way. Yeah. And when I press the M and tell it to solve all the way to the start, you'll see what it chooses to do. Right? So it's gone off looking for a short route over there and not found one, but it's still looking. Okay, and at some point around about here, it would have found a green cell and it could have done a fast run back to the start. If I set the target back to the center, which is what I would do with the mouse, we can do a for real run from the start to the center. It won't be the fastest run, but I get some diagnostics out when I do this, and I can see how long it has taken, how many cells it has moved, and how many turns there have been, which is the sort of thing you want to know when you're solving a maze. Okay, so that run took just under 16 seconds and moved through 96 cells, and there were 50 turns. So we're running, I don't know, 4 or 5 cells a second in terms of solving time. And that's with me doing all this printing out. If I turn off some of the printing, it can do it even faster. So it's quite fast enough to keep up with the mouse in real time. And I need to go back to the start again because I haven't found the optimum route yet. Having a look at places it hasn't seen before, because there might have been a route. And it's now actually picked up on a green cell and it knows its way home from here, but it doesn't run it any faster yet. Okay, so that was 21 seconds, 78 cells. I happen to know that's not the fastest route, so I will reset the target and do it again. Still not possibly the fastest route because the green cells don't go all the way back to the mouse. So it's going to have a look. Just it looked down here and found this crucial wall there, and now it's on green stuff and it can go fast. So that was 18 seconds, 72 cells, 50 turns. Let's do it again. And now it's on green cells now, I think. Probably difficult for you to tell because of delays in the system. I happen to know that 68 cells is the shortest route on this thing. So it's taken it 20 seconds to evaluate that route, 68 cells, and there are 30 turns. And if I do the same again, it'll just keep going backwards and forwards. So that is how it solves. Is everybody happy with that? Somebody stuck their thumb up. Good. Right. I'm going to reset what it knows and go back to the solver. Now, when you come to look for strategies for how you're going to solve a maze, you can choose as to whether the mouse is going to want to go straight on or want to turn. Now, this is strategy 1, and it puts the cells into the queue north, east, south, west. So it's going to grow up, to the side, down, and to the left in that order. Which means when it comes over here near the mouse, it's going to reach this cell before it reaches this cell. But there's a wall in the way, so it can't turn right, so it will come from here. If I do a couple of those, it's going to reach this cell before it reaches this cell, so the mouse will turn right. It will choose to turn right at this point. And that's what happens. Okay? That's what I call strategy 1. I can change my strategies. Strategy 4 is perhaps the one most interesting at this point. Reset everything. Now this puts into the queue this cell first. So it does west first and then north, east, south. So when I do the next one, you'll see it's growing this way first, which means it will reach this cell before it reaches this cell. So if I do the same as I did before, now it's going to choose to go straight on.
Duncan?
Yeah?
Sorry, your cursor doesn't actually indicate which cell you mean. Could you try and refer to them as the north cell or the east cell, or to go north or to go east?
So you're not seeing my cursor?
We see a cursor, but it doesn't seem to point at the cells that you mean.
Okay. Right, let's see if I can do that again. Right. So with this option, strategy 4, the search goes preferentially to the west. So it will reach the cell in front of the mouse, that's the 4th one up and the 1st one across, before it reaches the cell to the right of the mouse, that's the 3rd one up and the 2nd one across. So it would choose to go straight forward when it gets to the next one, like that. Yeah. So the decision of the mouse as to whether to turn or not will depend on the order in which you put the cells into the maze, into the queue. And there's, I don't know, a very large number of ways you can do that. I've implemented 8 strategies. I started off just doing northeast, southwest, starting with a different one. And that gives you these different things. If I show you the effect on the whole solve, So I'll reset everything, and I will do an M using strategy 4, right? So this is how it searches using strategy 4. And you can see that went basically up to start with. If I reset that and do strategy 1, that's what I was doing before, and it sets off in a completely different direction. Ends up coming back to the same point because that direction is useless. But you can see it took a lot longer. It takes a lot longer to get to the center of the maze this way. Okay. Now, strategy 7 and strategy 8 are more interesting because they make their decisions as to what to put into the queue depending on which way the mouse is facing. So I think strategy 7 prefers to run straight, so we'll try that. This would be a good strategy for a real mouse because it can probably run straight faster than it can turn. Strategy 8, it prefers to turn. And it does something different. Okay. When I'm getting at the bottom, I'm getting my time and the number of cells it moved and how many turns and that kind of stuff. So I can look at the data for the first run to find out which worked best. And you can play a lot of games with this. And because I can use Pete's Maze files, I can download those files and try them out. And earlier in the year, I had got 8 willing warriors to try them out with me after we'd written this thing. So, and particularly one of them, Miko, he wrote a Python script for testing them automatically, which was great fun. And the definitive answer as to which is the best strategy is I haven't a clue. So some mazes are solved better with one strategy and some mazes are solved better with another strategy. Now, unfortunately, this has implications. Certain maze designers might very well choose to design mazes that are optimized for one strategy or another. I remember Derek Hall tends to write solvers that turn right early, and Pete tends to write mazes that write solvers where the mouse goes straight on. And certain maze setters would favor one or the others for their own reasons. Now, what this means is if you know an awful lot about your maze setter, you might choose a strategy that solves the sort of mazes that they set more rapidly. Or you could cheat. You could set up your mouse so that when you set fiddler sensors in a particular way, it selects a particular strategy. And you could have a quick look at the maze and select a strategy before you run. This is strictly beyond the rules, but I don't know how you can stop somebody doing it if they want to cheat. Back in the day when we had a long, complicated rule set, you had to say what your starting procedure was for the mouse before you saw the maze. The mice were put into quarantine before any of them saw the maze. And you took the maze out of the quarantine and you put it into the maze, and you had to follow exactly the starting procedure that you had specified. These no longer appear in the rules. I don't know what to do about that. Perhaps we ought to discuss a rule change at some point as to whether strategy selection is going to become legal or not. But I don't know how you can prevent it. I think that's pretty much all I want to say, unless there's any questions.
It's been my experience that there is no good strategy. And even if you can see the maze and manipulate said strategy at the start, you're probably going to make a mistake. But eliminating the search penalty means that in a practical sense, it doesn't really matter if people pick one strategy or another, because it all comes down to how fast they can run it, regardless of how they got there.
Yeah.
The selection of strategy isn't as simple as just get to the middle. It's minimize the number of runs before you found the fastest route. And if you've only and if you've only got a short amount of time, that could be very relevant.
I would suggest then that when you do your return search, or whatever you wish to call it, you set the goal, the target, to be cell 1 rather than cell 0, and never re-enter the start cell.
Yeah. Yeah.
I don't understand why that makes a difference.
Because if you never re-enter the start cell, you've still only done the one run until you're happy that you found everything you need to find. Then you go back to the start cell and start your second run.
Yeah.
You only get 10 minutes or 5 minutes or whatever they've decided to let you have in the maze anyway.
Sure, but it's it saves you running out of runs. If you have a limited number of runs, you won't run out of runs.
Yeah. Do they have limited number of runs? Is it?
Yes.
Yes. Yeah, that's in the rule. That's in the rule set. Yeah.
Okay. Well, I mean, it's just a question of, as you say, don't do a run.
Yeah.
I remember when we told Billingsley that we were trying to reverse engineer his maze design. He was very freaked out. So we're trying to do exactly what you're talking about.
Okay.
Also, you get some of the entries that we've had in the past where they turn up with 10 mice that all look absolutely identical, but every single one would be running a different strategy with the thought that one of them is going to run the best strategy and therefore win.
Sure.
We do try and game the mazes are open to gaming, because an APEC maze historically, sorry Dave, has typically had 2 routes, and they always include long traits for the drama, and so that we set the mice up for APEC differently.
Okay.
One time we loaded every known maze into a database, and when you ran it, the solver, within probably 8 moves, it could figure out which maze it was, and then it would just go straight in. So but it was interesting that if you made enough changes, you kind of got screwed, because you would go off. We would be doing this maze matching, which gave you really wrong hints.
Right. Okay.
One question, sorry, just one more quick question. Duncan, do you, I'll ask you the other question some other time because it's going to be complicated, but as far as I can tell in your search algorithm, at no time do you calculate the cost from of the cell that you're in relative to the goal. You're only ever interested in what direction to go. Is that correct?
Yes. If you want counts, if you want to count cells back, you can have a count, and what you put into the cell is the count of the cell you came from plus 1.
Yeah.
But because you haven't explored all the routes, you've only explored some of the routes, because you don't put things in through the queue twice, you can't establish what the turns were.
Sure.
Because there might be another route to that cell that takes more steps in the queue, but has got fewer turns.